Good morning. I'm Mark Bowman, and I work for the Tennessee Valley Authority Nuclear Power Division, and it's my great pleasure to talk with you today about a very exciting project, something that I think is long overdue for the nuclear power industry, and that is using ETAP real-time as an online monitoring platform for a nuclear power plant. You know, TVA has had a very long history with ETAP, perhaps more than any other company out there. And in my industry, over 90% of the nuclear plants already use ETAP for their design work. But we don't use ETAP real-time. In fact, it really hit home when the CEO of ETAP asked us a few years ago, "Why don't you guys use this? When we invented it, we thought you guys would need it more than anyone." So I'm going to try and explain today why our industry, almost more than any other, has the need for this technology, but we also have some unique challenges that have prevented us from implementing it. And I hope what you get the most out of my presentation is how to make the case for using ETAP real-time by understanding all the potential benefits it can provide. And then I'm very excited to show you how TVA is implementing ETAP RT online monitoring systems for our nuclear plants. I want to say that a reliable source of electric power is critical to the safe shutdown of most nuclear reactors, and that's the moral of this story. So nuclear power plants have a lot of similarities, as it turns out, to large fossil fuel power plants. But one key difference is that they have this dedicated safety-related power system. Safety-related meaning essential for nuclear safety, to protect the health and safety of the public. And the purpose of this auxiliary power system is to provide mission-critical electric power to control the nuclear reactor, transport heat from the core, limit the accidental release of radiation. This safety-related power system is fed from off-site power like the grid, as well as on-site sources like emergency diesel generators and batteries. I know you probably can't see this one line very well. I just wanted you to get an overall feel for how the system is laid out. So, given that nuclear power plants have this very important auxiliary power system with a very important purpose, let's talk about the need for ETAP real-time. Now, as you probably know, ETAP real-time is a type of digital twin, a physics-based model coupled with real-time data. It's an in-plant state estimator, capable of producing system-wide data using only selected sensors. And it can be used for many things. It can be a complete power management system, capable of online monitoring, event playback, predictive simulation, system control, and many other things. But for a nuclear power plant, the real benefit that I'm going to focus on is online monitoring. And I'm going to show you how the additional knowledge provided by such a system has the potential to provide major benefits to nuclear safety, operability, and operating costs. So like I said, if this is so great, then why aren't we using it already? Well, there are some unique challenges to the nuclear industry that we need to figure out how to overcome. Since most nuclear plants already have an ETAP design model, that's not the issue. The real challenge is the fact that nuclear power plants were built prior to the digital age, and all the metering and instrumentation are in the form of analog gauges, like you see here in this picture. Here's your voltmeters and amp meters and watt meters. Here's some breaker indication. And all this was provided with no information of any kind that you can get digitally back to an ETAP RT system. I mean, I wish we could just plug in an Ethernet cable, but of course you can't do that. And because our industry is so highly regulated, any kind of changes or upgrades to add digital sensors is extremely expensive, much, much higher cost than other types of power stations. So now you probably see that's the name of the game. To justify the cost of installing the sensors needed for an ETAP RT system, we must build a case for that. And in fact, let's build a case on three fronts. A business case, because we always know we have to have a business case for anything we do. A nuclear safety case, and an operability case. So what I'm going to do over the next several slides is to show you some real-world things that have happened at my nuclear plants. And my point in this is to use these real-world events to build a case for ETAP real-time, how having an ETAP RT system would have improved the outcome in this area. So let's talk about the nuclear safety case. This first example involves a loss of offsite power at our Browns Ferry nuclear plant caused by a series of tornadoes in North Alabama on April 27, 2011. And you can get a feel for some of what that day was like here in these pictures. It was a bad day. But again, my point as we go through what happened this day is to be able to leverage what benefits to nuclear safety could have been realized if we had only had an ETAP real-time system. Here's Browns Ferry nuclear plant, and you can see the plant here. Here's the switch yard and the power lines. All the units here generate into the 500 kV grid. We have 7 transmission lines, 500 kV, that go out into all parts of the system, and there's also 2 additional 161 kV lines for offsite power. April 27th, 2011, and of course, all great stories start out with, "It was a dark and stormy night," and it was quite literally true that day. This was a very bad day. There were multiple EF4 and EF5 tornadoes rolling through North Alabama. In fact, this was the most damaging event to the TVA transmission system in history. 850,000 customers without power, 353 transmission structures damaged, 90 were completely destroyed. More than 100 transmission lines were lost, and it took 4 to 5 weeks to restore the transmission lines for the nuclear plant. But the key thing about this event is there was no major storm damage to the nuclear plant itself or to the switch yards. The plant was just cut off from the transmission system. And that's what's known in my industry as a loss of offsite power. The ability to power the safety-related buses from the transmission system has been lost. And those buses are transferred to the on-site emergency diesel generators, and they're designed for that. But it's classified as a serious condition by local, state, and federal emergency response organizations. To kind of put this in perspective, when this happened, it had been less than 2 months since the Fukushima Daiichi nuclear disaster, which was, by the way, caused by a lack of all power to the safety systems. So the situation we have, this is a serious nuclear plant emergency condition. We have to restore offsite power. Some transmission lines were still available, but the capability was unknown. Without SCADA out on the transmission system, the supplier took 3 days to investigate, repair, and determine the grid capability. And there are no plant engineering studies for this current plant condition because it's not a worst case. And it took 2 days to manually perform ETAP analyses to determine what is the minimum required grid capability for this situation. Now, we eventually determined that adequate grid capability had been available all along, and offsite power was restored, and the emergency was exited. So that's the good news, but it took several days. And what I'm trying to point out here is the knowledge provided by an ETAP RT online monitoring system, if we had had one, could have allowed us to use offsite power about 3 days earlier, greatly improving nuclear safety for this event. Now let's talk about the case for improving operability. And by the way, what operability means in my industry is the ability to operate within your plant licensing requirements. If you have operability, you're allowed to operate legally. If you don't have operability, you have to shut the plant down. And that's a large loss of generation and money to the company. And for this case, I'm going to talk about the Watts Bar hydro plant fire that happened in September of 2002. And here you can see Watts Bar nuclear plant. There's 2 units that generate into the 500 kV grid. Here you can see the 500 kV switch yard. However, what's kind of unique about Watts Bar nuclear plant is offsite power comes from a neighboring hydro plant. And you can see here in the picture, this is the Watts Bar dam. And there's 2 transmission lines that come across the hill here and over to the nuclear plant to provide the safety-related power. So the nuclear plant safety buses are directly fed from the hydro plant from the lines that are about a mile long. So let's go to September 27th, 2002. And you might be thinking, how can you have a fire at a hydro plant? I mean, it's basically concrete and steel and water. And this was actually in the FEMA report from this event. Many people perceive a steel and concrete structure as not being a fire risk. Well, that was not the case this day. The fire actually began in a 120-foot vertical cable shaft that you can see in the picture here. And it burned so intensely that the firefighters were unable to make entry for several hours. And we had extreme smoke and soot that was pouring out of this area up into the switchyard, and it's of course threatening the integrity of the switchyard, and that of course is the offsite power for the nuclear plant. And here you can see just how bad the smoke was coming up out of that cable trench, coming up into the switchyard. You can see it here. Here's the switchyard. Again, these are the lines that feed the nuclear plant. So what's the situation we're in? The nuclear plant still operating at 100% power with no offsite power supply. And operability is not met. And remember, I said operability means that you're legally allowed to operate the plant. And you can stay in this condition for up to 24 hours. But at the time, they were estimating that it would take 2 days to perform manual ETAP analysis to determine the adequacy of the remaining offsite power sources using the current plant conditions. And that's the key. Again, we don't have special analyses for these current plant conditions. Now in this case, we got lucky, and normal offsite power was restored about 19 hours after the fire, and we were able to exit the emergency operation. But like I said, the knowledge provided by an ETAP real-time online monitoring system could have supported continued system operability and saved an avoidable shutdown. And last, but definitely not least, is the business case. So for the business case, I chose just 2 areas: design margin recovery and event investigation. And what I'm talking about here is that ETAP RT data can provide data that will help you refine your design model. And for example, one of our TVA plants estimated that having data like this could eliminate some low margin issues on one of our critical safety related systems, eliminating a $1.1 million design change. What about event investigation? The ETAP RT playback can provide event data much faster than manual inspection. And just so you know, when we have events happen in our nuclear plants, it usually takes 2 to 3 shifts to go out and investigate what happened. And I'm talking about manually walking around the plant looking for what targets you see, what's the state of the breakers, do you smell smoke, what has tripped. And some of the recent events that come to mind are, we had a trip at Browns Ferry on Unit 3 in 2019. We had a diesel generator test failure in 2017 at Watts Bar. We've had multiple differential relay trips at multiple sites, 2012, 2015, 2016. So TVA estimates just saving that 16 to 24 hours of offline time per event would represent $800,000 to $1 million saved per event. So that's it. I've shown you how we were able to use some real-world events to build a case for using ETAP real-time as a platform for an online monitoring system in a nuclear power plant. Now, let's take a look at how TVA is implementing such a system for the first time. I'm very excited that TVA is currently underway with projects to install ETAP RT online monitoring systems on all of our nuclear power plants. That's 3 stations and 7 units. And we're starting with our Watts Bar nuclear plant. One thing we have going for us is we do have detailed, up-to-date ETAP design models that can become the building block for an ETAP RT system operational model. The primary users and stakeholders of this system are design engineering, plant engineering, our emergency response organization. So you may wonder, why just engineering? Why not operators? Well, in my industry, direct use by operators would have to be certified in accordance with plant licenses and operator training, and this would really just be impractical and cost prohibitive. And here you can see a picture I took just last week where the engineers and planners are out working on the design change package to start installing the sensors. And it's all about the sensors. I know it's kind of hard to see in this picture. This is a one line of the entire nuclear plant and the Watts Bar hydro plant and the Watts Bar nuclear switchyard. But you can see down here, this is our safety-related auxiliary power system. And really the name of the game in this project, as I've said, is to figure out where to install the sensors. And working with the ETAP engineers, we were able to come up with minimal sensor placement. You can see in the orange here, these are areas where we already had some digital data that was actually being supplied by the Watts Bar hydro plant. When it came to the nuclear plant, what was the minimum number of sensors we could put in? And I know it's hard to see, but these red dots show these are smart meters that are going to be on the feeders for the 6.9 kV switchgear. The blue areas down here are branch circuit monitors that we're going to place on the outgoing feeders of the 480 volt switchgear. And that's not too many sensors. Only 32 sensors in all have to be installed. And interestingly enough, the ETAP engineers figured out that we don't really need breaker position sensors. So for all the breaker positions, so we can know the lineup of the system, what boards are connected to what sources, we can actually use the power flows and the current flows and the voltage to deduce this inside the state estimator ETAP RT engine. So that was really an advantage. Here's just an overall view of our architecture. And you can see here are the ETAP real-time server and historical servers. All of this here is Ethernet. This is going to tie the system together. We've got the smart meters down here coming from the 6.9 switchgear. Here's the branch circuit monitors coming from the 480 volt switchgear. We're showing the PTs and CTs. Also PTs and CTs here that have to be connected to these sensors. But what I think is really cool about this, and something that I hope everyone realizes, is when you add up all these voltages and currents, we're talking about 32 points coming from the 6.9, 88 points coming from the 480, so about 120 points. That's all I'm sending. And what's the advantage of using a system like ETAP RT versus just any kind of online monitoring system is by using the digital twin concept, having that operational model coupled with all these data points, we're able to realize 15,000 points. So we get the whole system, all the power flows between all the buses, all the currents, all the breaker positions. That's phenomenal. And I think that is the main advantage, at least in our industry, for using an ETAP RT system over just going out and installing online monitoring of selected points. Now I'm going to show you a demonstration of the actual ETAP RT server that was built for our Watts Bar nuclear plant. We've built the server, but we haven't installed the sensors yet. So this is using simulated sensor data to feed the system. And here we go. And guess what event I've chosen for simulation? A loss of offsite power. You can see here this hydro line alpha has been lost. The buses have gone dead. The diesel generators have started. And here, any second now, you'll see them connect. Okay, yes, it's really easy to see on the screen. If you were a system engineer or a plant engineer, you can look at these human-machine interface screens and kind of see what's going on right away. The diesel generators are actually increasing in load now as they pick up the load on the bus. And one big point here is this system is providing all the data behind the scenes, not just what you see on the screen here. So you could drill down into these low voltage systems, you could look at more detail on this bus, and you're going to see all the power flows, the voltages, the currents, the frequency, and that type of information would be perfect for troubleshooting the system in case of whatever event happens. So that's it. We've seen how online monitoring of a nuclear plant's safety-related power system using ETAP RT can provide benefits to nuclear safety, operability, and operating costs. I hope that what TVA is pioneering in the nuclear industry can be useful to your industry as well. I have to say that I'm so proud to be leading this project at my company, and I think it has the potential to make a real change for my industry, more than any other improvement I've been involved with in my 30-plus year career in nuclear power. Thank you for your time today, and I hope you've enjoyed my presentation, and perhaps some of this will be useful in your industry if you're considering the need for an ETAP real-time system.